Well, I'm John Mather, and I'm the Senior Project Scientist for the James Webb Space Telescope at NASA Goddard Space Flight Center. So I want to tell you the story today of the universe from the beginning to the end, slightly abbreviated. So just thinking about what are the great questions of science over the years, astronomers have wanted to know for a very long time, how did it all start? How did the Earth form? How do the galaxies form? How do the stars form? How is it possible that the conditions for life could be formed here on Earth? What happens to stars when they die? Are there black holes? Yes, there are. Where are they? There is a black hole in the middle of almost every galaxy. And maybe even could we find out about the laws of nature? Are the laws of physics complete? So we have a lot of ways as astronomers to test these stories, and I wanted to tell you something about those today. So to start with, I wanted to say that there's always a surprise in life, and the surprise today might be that you are made of exploded stars. We have, as astronomers, have known this for a very long time, because where else could they come from? The Big Bang, which we now have known about since 1929, did not produce the heavy elements of life, so they must have come from something else, must have been the stars. So we now have a lot of details to figure out, but this is pretty much the truth. When you look in the mirror in the morning, you're looking at the insides of exploded stars. Pretty amazing. So if you'd explained that to Aristotle, he would have been amazed too. But then he would have said, but it is its nature. So how do we know all these things? Well, I want to tell you a little bit about that. The first thing is that astronomers, unlike most other scientists, really do look back in time. We see things as they were when objects emitted light and sent it in our direction. So we see the sun as it was about 500 seconds ago, the center of our galaxy as it was about 25,000 years ago, and if you could look almost all the way to the edge of the universe, you would see things as they were 13.7 billion years ago. So it's just to kind of see far enough back in time to learn what's going on. Now our penalty is that our view is really kind of fuzzy. We have to build a big telescope or a special instrument to be able to learn about these things that happened in the most distant times and places and farthest back in time. So, but that's what we do. That's what astronomers do. We build big telescopes and we look back in time. So how do we know how far we're looking? We do trigonometry, just like we might have learned in grade school or high school. We draw triangles and we say, well, if we know two of the angles of a triangle and one of the sides of the triangle, then we know the whole shape of the triangle. So this is basic surveying, and so astronomers do it too. And it works pretty well out to the distances of a few hundred or a few thousand of the nearest stars. After that, we have to be pretty clever about it. And beyond that, then it's better to do what we call the standard candle method. If we can see two stars that look alike to us, but one is fainter than the other, we say it's fainter because it's farther away. And we use the inverse square law for light to do this calculation. So this is now the basis for the measurement of the most distant objects that we can see. And it's a little tricky because measuring brightness for really faint things is tricky. But it's been the source of amazing discoveries. So next thing you'd like to know is, how does the universe move? Well, a few things move rapidly enough across the sky that you can see them do it. The moon moves its own diameter in a time you can actually watch. If you stay up all night, you can see it move quite far against the stars behind it. The planets, they move a lot slower, but they do move, and if you pay attention from day to day, you can actually see that they're in a different place every night. The most distant stars don't move at all, apparently, but we can still measure one thing about them. We can tell whether they're coming toward us or going away from us. And the way we do this is using what's called the Doppler shift. It's an effect that was noticed a long time ago. You can hear it yourself when you hear a distant train coming toward you, and then it goes past, and the pitch of the sound that you receive goes down as the train goes by. We have this similar effect for light waves, and so if we see a distant star and we spread out the light with a prism or a spectrometer and we get a nice little rainbow, we'll see markings in the starlight that say, well, this is a particular chemical or element or some other signature in the starlight, and we say, well, but it's at the wrong wavelength, and that's probably because it's coming toward us or going away from us. So we can tell this and measure the speed of motion toward or away, even out to the most distant objects. So back in 1929, Edwin Hubble had figured out how to do this for the most distant galaxies, and he had figured out how to see that there were stars in the galaxies, and even he found some standard candles in those distant galaxies, actually the not so distant ones. And so he was able to draw the first Hubble plot, as we call it now, where you plot the speed of motion of a galaxy against the distance. So he made a plot which was front page news in 1929, and he showed that the galaxies are going away from us, almost all of them, and with a speed that's about proportional to the distance. So if you divide the distance by the speed, you get the apparent age of the universe. That was the astonishing discovery of 1929. We remember 1929 for other reasons, because it's the year the great economy collapsed following the economic inflation that occurred in those days. Now we astronomers look back and say that was a special year for us as well. We discovered the expanding universe. Well, it had been predicted, actually, long before that. In 1916, Albert Einstein gave us the theory of relativity in general form, applying to gravity. And his equations now enabled people to calculate what should the motion of the universe be like. Before we had Einstein's equations, we had Isaac Newton's equations, and they didn't work for us. The calculations come out to be infinity, and you couldn't figure it out. So even Isaac Newton was aware that that wouldn't work. So, but in 1916, Einstein gave us these equations. In 1922, Friedman, working in Russia, calculated that the universe must be expanding. Then he died 3 years later. He didn't get to find out that his prediction was correct. His equations were calculated again in 1927 by Georges Lemaitre, who said that he believed that there was a primeval atom, that the universe came from this initial expanding phase, and so we should go look for it. And he actually calculated from some of the data that already existed at that time approximately the rate of expansion and the age of the universe that was measured a bit better 2 years later by Edwin Hubble. Georges Lemaitre was a theorist, and he didn't insist at the time that he'd discovered something. He said it should be. But in 1929, Hubble, who was an observer and everyone trusted him, he got the same answer, and everyone said, aha, the universe is expanding. This was a pretty great shock for the entire world. That was front page news. But now, you know, when people say, well, there was the Big Bang theory, it's not just a theory. We've known about it since 1929. So it is not just something we cooked up over beer to have a good time. So now I have to talk about how come we're here. Because the universe is expanding, and this great expanding thing doesn't look like it's going to stop expanding. So, but our universe that we see locally, the Earth, the sun, all the things that we see around us are not expanding. So our idea is that the initial material, whatever it was in the Big Bang material, had hot and cold spots, dense regions and less dense regions, and the dense regions had enough gravity to slow down the expanding material and cause it to stop expanding and fall back in. So this is a prediction from the Big Bang theory, and it actually has been verified. We have measured the hot and cold spots in the Big Bang, and we calculate that they're just enough so that the universe could stop expanding in places, and we would have matter falling in to make galaxies and stars and planets. So tremendous calculation success there, and observational prediction confirmed. I'll show you more later about it. So then, after the stars can form, then of course you can have the nuclear reactions that form inside stars, the hydrogen and helium that were left over from the Big Bang material. They can produce the heavier chemical elements of carbon, oxygen, nitrogen, everything we see here on Earth, produced inside stars. So when I told you that you could see the inside of an exploding star in the mirror in the morning, this is how we think that it worked. So now we can summarize the early history of the universe very briefly. We think that the initial expansion was kicked off in a sub microsecond by something we call inflation, and that's a whole large subject which I can't really go into. But after that, then the universe continued to expand, but to slow down for about 9 billion years, roughly 9 billion years. It took about 400,000 years for the initial material to become what we call a neutral gas rather than a hot plasma. So at that point it became transparent. And the primordial heat radiation, which we now observe as cosmic microwave background radiation, was then free to travel unimpeded from that moment until it reaches our detectors. So we're now able to make a map of the universe as it was when it was 400,000 years old, with using the cosmic microwave background radiation. So then what happened after that? Well, a couple of 100 million years additional passed before the gas had cooled enough that stars could possibly form. And now we're looking for signs that that actually happened. We know that we're here. We know that the chemical elements show signs of having been liberated very early. The most distant galaxies we can see already look a bit old. So we calculate that this must be so, but we've never seen it happen. So it's a great mystery what happened in the first few 100 million years of what we call the cosmic dark ages, before there were real stars and galaxies. So then after that, the universe continues to expand. About 9 billion years after the beginning, the Earth was formed. So we're only 4.5 billion years old, roughly. The Sun and the Earth were born together. Roughly about the same time, something quite remarkable happened also. And this was a tremendous surprise. The universe is accelerating now. It's going faster and faster every year. So what is this caused by? Well, we call it the cosmic dark energy, and we don't know what it is, but we have a name for it. So that really means we're ignorant. But that's okay. It's something to work on. So now I want to tell you something about how did we learn about the hot and cold spots, about the cosmic background radiation. Back in 1970, I was looking for a thesis project at the University of California at Berkeley, and the cosmic microwave background radiation was already detected in 1965, and we were pretty sure that it is actually the remnant of the Big Bang. But plenty of things were unknown about it. There were a lot of mysterious measurements that were probably wrong, so a graduate student would like to make a thesis project measuring this. Well, I did a project at Berkeley, and my culminating effort was a balloon payload, an instrument that carried aloft to about 140,000 feet on a long string hanging under a big balloon. And you know what? It didn't work. So I thought, this is way too hard. When I finished my thesis, I got out and I said, I'm going to become a radio astronomer. But that didn't work out so well because NASA said shortly after that that they wanted proposals for new satellite missions. This is 5 years after the moon landing, and so what is NASA going to do? Well, I said to my advisor, you know, my thesis project failed, but it should have been done in outer space. So he said, yes, that's true. We'll get our friends together and we'll write a proposal. And that turned into the Cosmic Background Explorer satellite, which was actually launched 15 years later, November 18th, 1989. So what did it measure? It measured several things. Number one was it measured the spectrum of this cosmic radiation to see if it really is, as predicted, the remnant of the Big Bang. And it should match up with what's called a perfect blackbody, that is to say an ideal radiating object, and it does. The eventual measurements showed that it matches predictions within 50 parts per million. So this was pretty much the end of competing theories. No other theory besides the Big Bang could produce such a perfect spectrum that we observed. The second remarkable thing that we found is called the anisotropy, which is a Greek word, and it means not the same in every direction. And what we did to do that was to make a map of the sky showing how bright is the cosmic radiation in each direction. So what we found was it's almost exactly the same, as it should be if it's really cosmic. And then there are a couple of effects. One is it's a little bit brighter in the direction of the constellation Leo than it is behind us. And that's because we're moving relative to the rest of the universe. So we're feeling the Doppler shift ourselves of this cosmic radiation. We subtract that effect, though, and we are left with hot and cold spots, very, very, very faint. The temperature of this radiation is about 3 degrees above absolute zero, which is pretty chilly, but it still comes out to 3 microwatts per square meter falling on the Earth. So that's actually a lot. It's just hard to measure. So anyway, we found these tiny hot and cold spots, which are only a few hundred microkelvin in brightness. So an extraordinary tour de force of experimental science to discover these things, and now these are the objects which we now believe are the ones predicted by the Big Bang, that are the required hot and cold spots that will grow up to become galaxies and clusters of galaxies. So if those weren't there, we wouldn't exist. Now also we have a wonderful additional surprise. We think that most of those hot and cold spots are caused by cosmic dark matter, which is another mysterious thing that astronomers can detect and nobody else has ever seen. So when Stephen Hawking saw our map, he said it was the most important discovery of the century, if not of all time. So I thought at first, well, that's just very generous of you, Stephen. But now that I've come to understand that we couldn't exist without those hot and cold spots, now I think maybe he was right. So now we have this great mystery partially explained. But we still have this great mystery in front of us. Well, what happened then? So we would like to know about this cosmic dark age when the first stars and galaxies may have formed. So how are we going to find out about that? Well, the Hubble telescope has shown us from its extremely long exposures, just pointing in one direction for several weeks at a time, that there are really, really faint galaxies as far as it can see. And the farthest away ones are within maybe 1 billion years of the Great Explosion, the Big Bang itself. But there's still more out beyond that. We can be pretty sure from what Hubble shows us. And the Hubble will not be able to show them to us because two things. One is they're too faint, and one is that they're so far away that their wavelengths have shifted out into the infrared. So the Hubble can't measure those infrared wavelengths well enough, and we need to build a new telescope called the James Webb Space Telescope that can pick them up. So the new telescope has to be bigger, more powerful, and colder than the Hubble Space Telescope in order to open up this new territory of science. So I'll tell you more about the telescope in a little bit, but before I do that, I wanted also to say something about the infrared light itself. Infrared is like ordinary light that you can see with your eye, but just the wavelengths are longer. And so we can't see them, but we can feel them with the temperature sensors in our skin. If you're a rattlesnake, you can feel them and actually make a kind of image so you know who to bite. But we don't feel it well enough to be able to sense it and see the most distant galaxies. So what we have to do is to build a very large, very cold telescope and have amazingly new and better detectors than we've ever had before that can turn a photon of infrared into an electron that we can pick up and count and send back to the ground by radio, so we can make a picture of that early universe. Something else that we, of course, realize is that the telescope has to be cold so that it doesn't glow. If it were warm and it would glow like we do, then it couldn't, of course, be a great telescope for infrared. On the other hand, because it picks up infrared, it can pick up things that radiate like we do. In fact, the telescope is so sensitive that it could take a picture of a bumblebee at the distance of the moon, just based on the heat that the bumblebee sends out. So that's one of the things that we can do that will help us learn about things that are farther away and fainter than ever before, and even see things that are colder than we've ever been able to take pictures of properly before, because we didn't have the equipment to do it. So this is a new territory of astronomy. We have other telescopes in space that can measure infrared, but they're not nearly powerful enough to answer all of our questions. So now I'm going to tell you something about how the telescope itself works. It is made in a folded configuration. The telescope needs to be much larger than the rocket that will carry it into space. So this is a kind of origami telescope, or a ship-in-a-bottle kind of telescope, where you have to fold it up very snugly after it's in outer space and protected and no longer being subjected to the wind blowing by from the rocket launch. We take the covers off. We send the commands to the motors to unfold this great telescope. And so several things will unfold. There will be solar cells to pick up sunshine to power the telescope. There'll be an antenna to send light back, send the information back to us and to receive the commands from us. There will be the great telescope itself that unfolds, pops into place, and then will be adjusted to the right shape. There will even be a giant umbrella that's composed of 5 stacked up layers of thin plastic, metallized plastic, that will reflect away the sunshine and enable the telescope to cool itself down to very low temperature all by itself when we put it in outer space. And to make all of this happen, we have to put it far away from the Earth. It'll be about 1 million miles away from the Earth, orbiting a place we call the Sun-Earth Lagrange point. So it's overhead at midnight, so it's in a line. If you take this line from the Sun to the Earth and go another 1 million miles, that's where the Sun-Earth Lagrange point is, and our telescope will orbit around that spot. So it's a perfect place for us. The telescope stays there for years and years, but we do have to keep nudging it to keep it there. Anyway, it's a good place, and it enables this telescope to work. On the other hand, we have to admit that it's too far away for the astronauts to go there with any technology that we currently have or expect to have in the foreseeable future. So we have designed this to be protected against that need. We have redundancy. We have 2 of everything where we can, and we've protected it, and of course we have to test it a lot. Anyway, now let me talk about what is the instrument package that it carries. We have 4 different instruments that come from around the world, because this is a partnership being led by NASA, but with huge contributions from European Space Agency and Canadian Space Agency, so that the worldwide science community will be able to use the telescope as well as the worldwide engineering community is building the telescope. So, by the way, it will be launched in 2018 to this Sun-Earth Lagrange point, and the Europeans are actually contributing the rocket launcher. So we will take the telescope down to their launch site in French Guiana in South America. So the scientific objectives of the observatory include everything from the beginning to now. We would like to see how the Earth came to be from the initial conditions of the universe. So starting with the Big Bang picture and the story that we have about the hot and cold spots, we would like to see how were the first objects formed. Prediction says that they were supermassive stars, maybe 100 times the mass of the Sun, and each one would burn out in about 3 million years and explode, producing the chemical elements that would then enrich the material out there and enable the formation of future generations of stars in a different way, and also the formation of stars with planets like ours. We've known now for a few years that it's possible to do it, either by taking a picture directly, where you have to work quite hard to block out the light of the star, or in a very special occasions, once in a while a planet goes between us and its parent star. So it blocks some starlight, and on the way through the atmosphere of that planet to our telescope, some of that light can be absorbed. So we actually have evidence of the atmosphere of the planet around another star by what we see in our telescope. So we've already proven this technique. We can do the chemical analysis of another planet's atmosphere by this method. So we already know of at least 1,000 candidate objects, some of which might be a little bit like Earth, going around a star that's a little bit like the Sun. And so we hope to learn something about them. We are very interested in getting the closest possible target stars, so a survey of the entire sky that could show the nearest stars that have planets doing this, as they're called transiting planets, is of great interest to us, and I think will enable tremendously exciting surveys in the future. So we'd like to see also the assembly of galaxies from small bits into large ones. If we believe, as claimed, that the first objects were just stars, well, were they clustered together in groups? Were they formed in groups of maybe tens or hundreds or thousands or millions? And if our current story is correct, they actually formed in groups of thousands or millions. But that's very small compared to our current galaxy, which has 100 billion stars in it. So we'd like to see, how did this happen? So we look far away to see what were galaxies like a long time ago. So what we see is that some of them are like today's galaxies, which means really we didn't get to see far enough yet in their history. But a lot of others are very small and diffuse and irregular. And we calculate that they will collide with each other. And just as galaxies are still colliding, in fact, our Milky Way has two tiny galaxies called the Magellanic Clouds, which are currently in the process of falling in to join the Milky Way. So we'd like to see if this history that we think of actually applies to what we see far back in time. Another great mystery is every galaxy we see today seems to have a black hole in the middle, but astronomers are almost completely mystified as to how this happened. We think that some of the stars that exploded early on could have formed black holes, but only tiny ones by comparison with what we see today. Some galaxies have black holes in the middle that are a few million times the mass of the Sun, and our galaxy, the Milky Way, has one of those. Other galaxies have central black holes that are hundreds of millions or billions of times the mass of the Sun, and it's almost impossible to understand how this could happen. So we have, however, chances to see the evidence of this happening over the course of time. Closer up, we anticipate looking inside the clouds of dust and gas where stars are being born today. We know in beautiful places like the Andromeda Nebula and the Eagle Nebula, where we've taken amazing pictures with the Hubble, that we see clouds of glowing gas, and we see that there are bright stars nearby that were born inside. They could only last for a few million years themselves. So we know it's happening today, but we can't see it happen. And the reason that we can't see it happen is that the telescopes we have observe visible light, and the visible light is blocked from our view by clouds of dust. We just can't see inside. So we can use infrared, however, and that is one of the great objectives of the new telescope, is to see inside those clouds of dust and gas, to observe the formation of stars and planets directly. There will be places, we think, where we can see a planet forming around a star, but we have to be a little bit lucky to catch it in the process, because it doesn't last very long. Closer even than that to home, we anticipate our users will point the telescope at the planets in the solar system, at the comets that come flying by, at the little tiny remnants of the early of the early solar system that are still orbiting around in the asteroid belt and the Kuiper belt. So all of these are bits of evidence of how our solar system formed and changed through time. And we're especially interested in what was it that fell onto the Earth to bring the water that we currently have and the things that make it possible for us to live here. Earth is like Venus, but not exactly. It's a little less like Mars, but not exactly. So how is it that Earth has ended up in this special condition where it has not only the right temperature, but also the right chemical constitution, and the water is on the outside and the air is on the outside, and so we like it here. And so far, there's no other place that we've found in the entire universe which is like this. So how does this happen? Well, it's one of the great mysteries that we're currently working on. We make a little progress. And then, of course, our friends that are building missions to actually go to other planets, they can only go within the solar system, but we have a rover on the way to Mars as we speak. We'll land and we'll drive around and pick up rocks and try to do some chemical analysis, and maybe even collect some samples that will be brought back by a future rocket to the Earth for our more detailed understanding. So we have a lot of possibilities to learn about the formation of life elsewhere in the solar system. And meanwhile, our biologist friends are trying to make it happen immediately right here on Earth in their test tubes. So one of these days we may have some answers to how did it all start and how's it going to end. Oh, and I forgot to tell you how it's all supposed to end according to astronomers. In the end, the universe will continue to expand because it's accelerating now. And it probably isn't going to stop, although we don't know that. And when it continues to expand, all of the stars that we currently know of will die. Their material, some of it will come back out into outer space and be recycled into future generations of stars. But after enough billions of years have passed, then we think all of the stars will die. So it's a good time to be alive as an astronomer right now. Thank you very much.